We're starting a new topic. In fact, we have two small topics that we want to discuss before we get to our next main topic, which is linear transformations. So the topic of this lesson is invertible matrices. So I'm going to define it. I'm going to do some examples, write some theorems, but we're not going to do all the details. We're treating this rather as an auxiliary topic, which is necessary for other things we do. Likewise is going to hold for our next little topic, which is determinants. So here's the definition. Let A be a square matrix. So all of this discussion is only going to relate to square matrices, namely that they have the same number of columns as the number of rows. Okay? A is called invertible. That's what we're defining. If there exists another matrix, let's call it B, such that A times B equals the identity matrix. Okay? And A is going to be a square matrix, say n by n. B is going to be another square matrix, n by n. And I is going to be the identity matrix of size n, namely n rows and n columns, ones along the main diagonal, and zeros everywhere else. Okay, so that's the definition of an invertible matrix. And you can see that it's just like we had inverses for multiplication in any field that we discussed, right? What is an inverse? An inverse is something that you multiply by and get 1, right? So this is kind of the same idea, okay? So here are two remarks. In fact, they're theorems. In fact, they need proof, but I'm not going to prove them. I'm just going to state them as facts. The first one is, if AB equals I, so if A is invertible and B is what we're going to call its inverse in a minute, and the product is I, then BA equals I as well. Okay, so if there is such a B, in fact, it works for both sides. Okay, in general, remember that AB and BA in general could be two completely different things in matrices, even if they're square matrices. Okay, so there's no commutativity for multiplication of matrices. But if their product is the identity, then there is this commutativity just in the realm of invertible matrices. Okay, so that's the first comment. And the second comment is, if A is invertible, and it's an if. We'll see in a minute in examples that not every matrix is invertible. But if it's invertible, then B is unique. So if there is such a B, such that AB equals I, then there's only one. There can't be two different ones. Okay? And that is the reason, this uniqueness property is the reason that we call B the inverse matrix. Okay? Because there's one. If it's invertible, then it has a inverse matrix, but in fact, it's the inverse matrix. So let's write that. Let's call it notation. The inverse matrix is denoted by A to the power minus 1. And it's called A inverse. Okay, let's write that. called A inverse, or the inverse matrix of A. Okay, so that's that B. Okay, let's do some examples. So here are some examples. Here's the first example. Let's take A to be a 2 by 2 matrix, everything nice and small and easy to handle. 2, 1, 4, and 5. So the claim is that A inverse, then this matrix is invertible, and its inverse matrix is the following: 5 over 6, negative 1 over 6, negative 2 over 3, and 1 over 3. This is A inverse. Okay? So what does it mean that this is A inverse? I have to show you that if I take the product of A and A inverse, I get the identity. Okay? Let's do it. So A times A inverse. If I claim that this is A inverse, I should get the identity. And this is just a matter of calculation. We know how to multiply matrices. So let's do it slowly and see what we get. So 2 times 5 over 6 is 10 over 6, which is the same as 5 over 3, minus 2 over 3. 5 over 3 minus 2 over 3 is 3 over 3. So in the 1, 1 coordinate, we get a 1. What about the 1, 2 coordinate? It's this row times this column, right? 2 times negative 1 over 6 is negative 2 over 6, which is negative 1/3, plus 1/3, we get a 0. Good? Everybody remember how to multiply matrices, right? This is something by now you should feel comfortable with. 4 times 5 over 6 is 20 over 6, so it's 10 over 3 minus 10 over 3. So here we get a 0. And finally, minus 4 over 6, minus 4 over 6, which is minus 2/3, plus 5/3, minus 2/3, plus 5/3 is 3/3, which is 1. So we indeed got the identity matrix of size 2. Okay? So indeed, this is the inverse matrix of A. Okay? And I want you on your own verify that in fact A inverse times A gives you the identity matrix as well. Okay? It's a similar calculation. Just do it. Make sure that it in fact holds. Okay? Now, this raises a question. How did I find this? How did I determine that indeed this is an invertible matrix? And where did this come from? Answer, it was on my paper. But how did it get there? Okay, so that we still have to answer. That's going to come up next. But let's do another example first. So the claim is that the matrix A, again, a 2 by 2 matrix, 1, 1, 2, 2, is not invertible. Why is this indeed the case? How do I know that it's not invertible? We're on this board, please. How do I know that it's not invertible? Well, if it were invertible, then there would have been a matrix, the inverse matrix, call it A inverse, such that the product gives you the identity. Okay? So let's try to take any matrix, for example, A, B, C, D. This is the most general form of a 2 by 2 matrix. And let's assume that we indeed, in the multiplication, get the identity. Okay? If such a matrix exists, then in fact it is invertible. And if it doesn't exist, then my claim is correct. It's not. Okay? So, is there a solution to this system of matrices, you can call it? Okay, is there such a matrix? Well, if there is, this yields a system of equations. What system of equations? A plus C should equal 1. Okay, A plus C should equal to 1. Do you agree? And B plus D should equal 0. And 2A plus 2C should equal 0. And 2B times 2D should equal 1. So if there is such a matrix, this system should have a solution. And obviously, this system does not have a solution. For example, equation 1 and equation 3 contradict each other, right? If here A plus C is 1, and here by dividing by 2, we see that A plus C is 0, that cannot happen simultaneously. Okay? So no solution. No solution to this, hence no solution to this, hence there is no A inverse. There's no matrix you can plug in here and get the identity. Do you agree? Okay? So just to remark about this, so first of all, you see that in fact there are matrices which are not invertible. Okay? And what we will want to do is characterize those that are. Figure out how do we know if a matrix is invertible or not. And this is a 2 by 2 case. This is the easiest possible thing you can do. What about a 7 by 7 case? Okay? And the remark that I want to make is that in fact, this is a way of determining if a matrix is invertible. Write your general matrix here and see if you can solve the system. If you can solve it, if you can find a solution, then that's it. It is invertible, and if it doesn't have a solution, it's not. Okay? So note that this is a method for determining if A is invertible and finding A inverse if it is. Right? So why am I writing this as a side note and not saying, hey, here's the answer to our question, how do we know if a matrix is invertible and how do we find A inverse? Because there are better ways. Okay, so this is kind of the long way to do it, which is correct. You could do it like this, but there are more efficient ways of doing it, and those are going to be called a theorem, and we're gonna discuss them soon. Okay, so is it clear? Is everything questions so far? Everybody good? Okay, so let's write before we get to that. Before we get to the general method of determining invertibility and finding A inverse, let's write a little short theorem. And in fact, let's prove it. We are going to prove some things just to get the feeling of how we prove things and what are the tools and get used to working with invertible matrices. So it's going to have two parts. The first part is if both A and B are invertible, so we're taking two invertible matrices, then their product, AB, is also invertible. And we even know what the inverse of the product is. So AB inverse, that's how we denote the inverse of a matrix, right, equals to the inverse of B times the inverse of A. Okay? Now, the fact that when we did some sort of operation, it reversed the order, this is not something we have never encountered before. We have seen this, do you remember where? With the transpose, right. When the transpose of a product was the product of the transpose matrices in reverse order. Okay, and we even proved that very long ago when we had the properties of matrices and we defined the transpose and multiplication and everything. Okay, and the second part of the theorem relates to the transpose. If A is invertible, then A transpose is invertible, and the inverse of A transpose, the inverse of the transpose matrix, is the transpose of the inverse matrix. Good? So how do we prove theorems like this? Okay, so let's in fact prove them. So proof. Let's prove one. So what do I want to show? I want to show that the matrix AB is invertible and that in fact its inverse is this. In order to prove that a matrix is invertible, I need to show that there is some other matrix such that if I multiply it by it, I get the identity. And here it is. The claim is that this is it. This is the inverse. So if we show that AB times this equals I, then we're done. We proved that AB is invertible, and we proved that the inverse is in fact this. Okay? So I'm taking AB and multiplying it by the candidate for being an inverse, by B inverse, A inverse. If I get I, I'm done. It's invertible, and this is the inverse. Good? So we know that when we multiply matrices, we don't have commutativity, but we have associativity. So this can be rewritten as A, B, B inverse, A inverse. What is B times B inverse? I, because B is invertible. So this equals A I, A inverse. Multiplying by I is like doing nothing, right? I is the identity matrix. So this is A inverse. And what is A times A inverse? I. So again, look at what we did. This is the key here. We took the matrix AB. We took this matrix, whatever it is, and show that when we multiply them, we get the identity. That means that AB is invertible, and that its inverse is this. Its inverse is this. Good? Here's the proof of part 2. The proof of part 2, same idea. I want to take A transpose, multiply it by the candidate for being its inverse, and see that I get the identity. If I do, I'm done. Okay? So take A inverse, multiply it by this. This is what I claim is the inverse of A transpose. Sorry, I said A inverse, right? Take A transpose, multiply it by this. So times, in fact, I don't need the parentheses here. A transpose times A inverse transpose. If I get the identity, I'm done. Is the logic clear? I think this is the only thing to understand about this proof is the logic behind it. Is the logic clear? Okay. So how do I do a product of transpose matrices? We said it just a few minutes ago. Right. It's the reverse order of the original ones, transpose. So it's A inverse times A transpose. Right? So this is a previous theorem about what is the transpose of a product. And now A inverse times A is I, because we made a remark earlier that if A inverse is I, then so is A inverse A. Therefore, this is I transpose. And the transpose of the identity matrix is itself. So this completes the proof of both parts. Good? Okay, so I think this is a good point to pause, and in the next clip we're going to discuss the issue that we raised as the core issue of this topic. How do we determine if a matrix is invertible? What are kind of characteristics? Okay, how do we characterize an invertible matrix? And if it is, how do we, as efficiently as possible, find A inverse? So that's the topic of the next little topic in this subject.